Introduction to hypothesis testing. Welcome to hypothesis testing class. In this class, by the time I'm done, you should be able to identify the 4 steps that are involved in hypothesis testing. You should be able to define what the null hypothesis is, what the alternative hypothesis is, what a level of significance, a t-test, a p-value, and a statistical significance, what all these imply. Further, I will explain the 2 types of errors that we have. We have the type 1 and type 2 error, and how to identify the type 1 and type 2 errors. We also calculate the z-test and interpret the results. And finally, I'll take you through distinguishing a 1 from a 2-tailed test. A 1 from a 2-tailed test. So hypothesis testing is one of the most applicable topics in quantitative methods where we want to test a claim. Hypothesis testing is mainly used to test differences that exist between 2 means. One has a claim, and how do we test the difference between 2 means? So I'm going to simplify this with a few definitions. So I'll send you the notes on the group afterwards so that you're able to follow at your own time. So what is hypothesis testing? Hypothesis testing is simply testing a claim. Whenever people have assumptions, for instance, now that we are having COVID, that on a daily basis we are having 1,000 infected, then when we go into the field, we discover that they're actually 10,000. So the 1,000 claim that the Ministry of Health is giving us against the 10,000, we have enough evidence to rebut or to construe the available assumption that is there. So really, when we're dealing with hypothesis testing, we are measuring the differences between 2 means. One mean is hypothetical, it's a claim, and another mean is statistical, it is calculated. So, like I said, if on a daily basis it is claimed that 1,000 people die, then at the hospital, when we sample out, maybe we find that 1,500 are the ones dying out of a number of 50 towns. So the 1,500 is statistical mean because it's actually calculated from the 50 hospitals. The 1,000 is simply an assumption. So the difference clearly here is 500. Now this 500, we either want to make it significant or insignificant. So whenever we reject our null hypothesis, it means that these people are lying. The 500 difference is big enough to accuse them of having a wrong statistical figure. But when we fail to reject, it means the 1,500 and 1,000 as one and the same. This is a negligible difference. So whenever we're dealing with hypothesis testing, we have what is called the null hypothesis and the alternative hypothesis. So you always need to formulate 2 hypotheses. The null is the original claim. The alternative hypothesis is the opposite. So when you are dealing with the null hypothesis, our HO is our original claim. So the hypothesis we want to test is called HA. This is the likely true hypothesis. So there are 2 possible outcomes where we can either reject HO. By rejecting HO, it means we're accepting HA. Whenever we accept H, it means there's a significant evidence in the sample that will favor our alternative hypothesis. So in short, if we have an hypothesis to say 1,000 bodies die in a day, if we reject our hypothesis, it means no, more than 1,000 actually die, all right? Or less, and depending on how the hypothesis has been. If we do not reject HO, it means that we don't have enough evidence to dispute that those bodies that are dying are indeed 1,000. So this topic is very easy. I want to take my time. So hypothesis testing will require us understanding 4 key important steps. We need to understand 4 key important steps that are involved. So hypothesis testing, like has been mentioned, is simply a method of testing a claim or an assumption about a certain parameter in a population. So assumptions vary. Today, I must say the most important people that need to be very sure about their claims are doctors. Amidst this pandemic we have, how sure are they that this diagnosis they've given you is not COVID or COVID related? So to identify a claim that has to be tested, you need to understand hypothesis testing as doctors. That's why this is one of the faculties that involves more key decision making programs or faculties. Those that are in finance, those that are in banking, and more so doctors need to understand this topic very well. So yeah, about 4 steps or 5 steps that are involved in hypothesis testing. Number 1, you need to state the hypothesis itself. Number 2, you need to set up a criteria for testing the hypothesis. Number 3, you need to compute the test statistic. And number 4, you need to make a decision. Now, with these 4 steps that are involved in hypothesis testing, I'm going to give you a table that you need to memorize. There's what we call level of significance. There's what we call the confidence level, which is CL. SL is significance level. Alpha is the decimal of the significance level. And our Z here, alpha over 2 is for a two-tailed. I'm going to be as basic as I can be. So we have 4 common confidence levels. Any level above 50% is called confidence level. How confident are we? For 99% confident, meaning the significance level is a difference from 100. So what becomes our significance level here? 1%. Then when you divide this by 100 in decimal, in short, when you convert this to decimal, it becomes our alpha, which is 0.01. And the Z for this one is 2.58. And when we go to 98%, what is the level of significance? The difference from 100, which is 2%.
Sorry, Collins, just before we go,
Uh-huh.
where are we getting the 2.58?
I'll show you how to get it for now. There are 4 steps that are involved in finding this. Okay, maybe before I go there, at least let's understand the three conversions. If we have 99, it's 1%, which is 0.01. I'll explain how to get this. If we have 98, it is 2%. What is our alpha here? 0. What? 0.02. If you have 95%, what do we have as our level of significance?
5%.
5%.
And our alpha?
0.05.
0.05.
0.05. Good. If we're not given the level of significance, this one is happening. It happens to be the standard one. In case you're not given a level of significance, this one is what we accept as standard. Then finally, 90%. What is our level of significance?
10%.
10%. Then here we have what? 0. What?
0.1.
So our Z for 95%, I'll use 3 steps, 4 steps for 95%. So step 1, find the level of significance. What is the level of significance for 95%? 5%, right?
5%, yeah.
5%. And we'll be dealing with the two-tailed test for now. So since the two-tailed test, we're going to divide by 2. So what is 5% divided by 2?
2.5%.
2.5%. Then we're going to subtract this from 100 because those tables are cumulative tables, they add up to 100 in total. So when you subtract from 100, what are we getting?
And 7.5.
Yes, we get 97.5. Then we're going to convert this into decimal. And 7.5% into decimal will be what? Divided by 100, what do we get?
0.975.
0.975. Okay. Now we'll go to the Z table to find the Z value of this one here. So the Z value, I hope you were here when we're learning how to read the table. So the Z table looks like this. So if you're getting a reading, for instance, like 1.23. If you have a reading like 1.23, this is our Z. We're converting it to the probability. So you go to 1.2 in this horizontal axis and 0.03 on the top here, where they're meeting is 0.8907. 0.8907. So this is from Z to the probability. Now, when you're being asked to convert from the probability to the Z, you're reading from inside the table. 0.8907 is equivalent to 1.23. So I'll ask 2 questions here. Give me what is the reading for 1.57. What is the reading for 1.57? What is the probability for the Z of 1.57? And also give
0.9418.
0.9418. Do we agree?
Yeah.
Okay.
Yes.
So let's check 1.57 here. So if I ask you now, 0.9418. What is the Z for that one? You just add the two figures, 1.5 and the one on top, 0.07. So this will be 1.57. Even if I ask you to convert the probability of 0.9417 here, the closest is still this one here. You'll still pick this number here. You'll give me 1.57. Now let me pick some number arbitrary. 0.9293. Give me the Z for 0.9293.
0.92.
Will it be 0.8238?
So 92, you read from inside the table, look for 9293. There's no 9293, but the closest is 9292, right?
Yes.
So what's a Z for this one? 9292?
1.47.
Yes, 1.4.
1.4.
Good. The Z is 1.47. All right. Now let's get back to our story. Our story as of now, we found firstly for 95%, we found our level of significance, which is 5%. Half of it is 2.5 from 100, 97.5, then decimal 0.9750, then finite the Z here. Let's look for it inside the table. Give us the Z for this one here. Let's go back to the table. What is the Z equivalent to that probability? It may not be exactly or the closest, or you may find the closest. So give me the Z.
1.96.
Okay, it's here. We have something exact, right?
Yeah. Yes.
1.96. So this is where the 1.96 is coming from here. Okay. Let's try for 90% together. Step 1, 90%. Step 1, find the level of significance, which is what?
For 10%.
Good. Then step 2.
We need to find the half of the significance level, which is 5%.
Good. 5%. Then
100 minus 5.
which is what?
95.
Then
We change the 95 into decimal.
which is
0.95.
Then
We find the Z score.
find the Z score.
Z value.
Z value, good, in the table. So we locate it.
The closest is 1.65. 1.65.
So 1.6. 4 and 5 are close. All of them. This one is low by 5. This one is above by 5. So what do we do in this case? You pick in the middle. So this is a 0.5. So you start with the smallest. So you are 1.645. Okay. The half is 0.05. So if it was between 6 and 7, it would be 1.65. All right. I hope you get, however, if you get any of them is correct. I just want it to be as precise as possible. To be more accurate, it will be 1.645 because the 0.5 means in between. So this is why this one will be 1.645. Although some books you find 1.65, others 1.64. Either of them is okay. 98%. Let's try 98%. Step 1. 98%, step 1.
We find the significant
2%.
level.
Step 2.
We find half of that.
1%. Step 3.
We subtract from 100.
99. Step 4.
We convert that into a decimal by dividing by 100.
0.99. Step 5.
Then we find the Z value.
Okay. Let's locate the Z.
So this one is 2.3, in between 0.02 and 0.03. So 2.3. 2.3 is 2. 2.3.
2.33. This one is closest.
33.
Yes. This one is down by 2. This one is down up by
Okay.
1. So exactly 2.33, isn't it?
Yeah.
So this is where the 2.33 is coming from. Now, if these are the standard ones, I'll need you to memorize them so you don't undertake this whole step. All right. So before I go into the memory state, I want you to find 97% on your own just now, and 7%. I give you 2 minutes. So if you've correctly done that, so you discover that 97% will be 2.17. So it's imperative that sometimes, besides the 4 percentages you're given, an examiner may be funny and give you any of the percentages outside what I've given you. Of course, those are the 4 common ones. But if you're given 97%, at least you know the steps that are taken. So we're dividing by 2 because it's a 2-tailed test. If it was a 1-tailed test, which I'll explain later, a 1-tailed test, a 2-tailed test means we are looking at it from 2 tails, this side and this side. This is a 2-tailed test. A single-tailed test means you're looking at it from 1 tail, either the right-tailed test or the left-tailed test. So for now, I'm just dealing with a 2-tailed test. Now, hypothesis testing has the following steps. You need to state the hypothesis, state the level of significance, state the decision rule, calculate the Z, and make your decision. Now, before we go any further, I need you to memorize with me the Z tables. So we have 99, 98, 95, and 90. These are the common ones. We have 2.58, 2.33, 1.96, and 1.645. The top 2 are consecutive with 2's in their Z, and the bottom 2's with a difference of 5 have 1's, 1.96, 1.645. So you may be given arbitrary. Sometimes you'll be given in terms of the alpha. What is the Z for 0.05? 1.96. What is Z for 1%? 1% is 99%, which is 2.58. So I'll ask you to memorize. So quickly, we have 4 common Z and 4 common levels of confidence. So let's start with the top one. We have 99, then Langiwe, 99,
2.58.
98,
2.33.
95,
1.96.
and 90,
1.64.
1.6645. All right, great. So uh, I will ask you to unmute your mics so that I do this exercise quickly. So I want to work with the memory. Yamikani, when I give you any, whether it's alpha or Z, I need you to just give me the Z values. Okay, Yamikani, 1%. Yamikani, 1%.
Sorry, Coins, I'm just trying to get the hang of it.
Okay. Patricia, 0.02.
2.33.
Yes, 0.02 is 98%, which is 2.33. Good. 10%, Mia, 10%. Daniel, 95%.
And is should be
1.96.
Yeah, 1.96.
1.96, good. 0.10. Bishop, I don't know. Bishop is who?
That's me.
That's who? Who is
Yamikan.
Oh, okay.
2.5.
Yeah. What is 0.10? 0.10. Langiwe and Patricia, 0.10.
2.58.
Okay, there's a thin line between 0.01 and 0.10.
Or 0.10. 1.645.
Uh-huh.
Sorry.
Then 0.01.
2.5.
Okay, great. So now let's get to business. So I'm going to simplify. We're going to test the following hypothesis. So our HO and our H1. So here our mu is 10. Our mu is not equal to 10. And then we're given a sample size n of 36. Our standard deviation is 12. Our alpha is 0.02. And finally, our x bar is 15. So hypothesis testing, step 1, state the hypothesis, which we already have. Step 2, the level of significance. So SL is 2% coming from here. Meaning our Z is what? Step 3, our Z is 2 point what? 2.33. So since this is a two-tailed test, the sign for a two-tailed test is this here, greater or not equal to or not equal to. So what this means is we are going to reject our hypothesis if it's less than negative 2.33 or if it's greater than positive 2.33. So this is called the rejection region. Whenever our answer falls in this shaded region, we call this the rejection region. And this is the accept region whenever our answer falls in here. So our comment will be, we're going to reject HO. We're going to reject HO if our Z calculated is greater than 2.33. Or if our Z calculated is less than negative 2.33. That's the comment. Step 4, calculate our Z. The formula for Z is given by X bar minus mu over standard deviation square root of n. So here, our Z calculated, what is our X bar? 15. What is our mu? 10. What is our standard deviation? 12. And square root of n, n is what? 36. So 15 minus 10 is 5. Square root of 36 is 6. 6 into 12, 2. 2 into 5, 2.5. Then you identify the 2.5. Where's the 2.5 in the accept and the rejection region? It is here in the rejection region. So our decision here will be what? To reject HO. While rejecting HO, it is in the rejection region. What is the conclusion? There is no significant difference. There's a significant difference. I said rejection region means there's a significant difference here. When we fail to reject, it is no significant difference here. Okay. Now let me fortify on this. Whenever we reject HO, it means there's a significant difference that exists between the two means. So evidently, 15 and 10 are different by 5. So we're actually testing the difference of 5. Now I want to see whether this 5 is statistically different from 10. So an examiner will say, it is assumed that 10 people get COVID in every wedding gathering. After sampling 36 weddings, it was with standard deviation 12. It was found that 15 people get sick of COVID. So now I want to test at 2% whether there is a significant difference between what the public health department thinks and what is actually on the ground. So we conduct a test. So number 1, state the hypothesis. Number 2, the level of significance is 2%. This 2% is what helps us identify our song. This is 98%, 2.33. So we shade here and there. We'll say we're going to reject only in these 2 areas. If our answer falls in these 2 areas, we're going to say, no, these people are lying. If it's not going to fall to be inside here, we say, okay, they're telling the truth. There's no difference between 15 and 10. So when we calculated 5 minus 15 minus 10, we found a Z value of what? Of 2.5. So 2.5 is in the rejection region here. If we found 2.1, those here would have said we failed to reject. It means 10 and 15 are not the same. So it is important to know the level of significance. So if our level of significance here was 1%, 1% is 2.58, which is here. And our 2.5 would have been inside. It would have changed the whole story. So here, our Z value is 2.5 in the rejection region. Sometimes we can use what is called the p-value. You're reading using 2.5. You go to the table and check for this 2.5. So when you go to the table, check for this 2.5 and you compare it against 0.02. Here it's the opposite that happens. Let's go and check 2.5. When we go to check the table under 2.5, the reading is 0.9938. 0.9938. So for the p-value, we compare it to this one. 0.9938. So here we reject if this one is we only reject if this one is greater than, okay, so which one is greater? 0.9938 and 0.02. We have our 0.9938 being greater than that. Okay, so we reject. So I'll teach you about the p-value more later, but for now, let's try an example together. Suppose our null hypothesis that we're testing says on average, it is assumed that a pumpkin from a big farmer, he claims that his pumpkins weigh 8 kgs. Okay, each. In our alternative hypothesis, maybe they don't weigh 8 kgs. Then when we sampled 64 of these pumpkins, 64 of these pumpkins, we found that they were actually weighing 6 kgs. So X bar is to the sample size. This is statistical mean. It was found that they weigh 6 kgs. Okay, with the standard deviation of 24. Test this at confidence level 90%. Test this at 90%. So let's go through the steps. Step 1, state the hypothesis, which is already there. Step 2, level of significance. What is our level of significance?
10.
10%. Step 3, what is our Z?
1.645.
1.645. Good. So since it's a two-tailed, we reject if it will fall at any of these extremes. Here, negative 1.645, and there, positive 1.645. All right. Then step 4, we calculate our Z. What's the formula for Z? Z is equal to what? X bar
X
minus mu
mean
over
standard deviation
root of what?
over root of n.
So what is our X bar?
6,
And our mu?
8,
And our standard deviation?
64.
24. And our N?
So our n is 64.
Okay. So the difference on top we are testing is the difference of 2 negative, right? Then 64 is 8. 8 into 24 is what? 3.
Yeah.
So Z is what? Negative.
Negative 0.6.
It is 0.67.
7.
So let's identify 0.67 is somewhere where? Here, right? Inside.
Yes.
So what is our conclusion? We fail to reject HR because it's inside. So we fail to reject HR. What is our conclusion? There is no statistical difference. 8 and 6 kg
6.
are more the same. So as statisticians, especially at masters, we fail to say accept, because by accepting, we are just saying 6 and 8 are the same. No, we just say we fail to reject it. We have no evidence to dispute you. So the means, there's no evidence that the means are statistically different. Okay. There's no evidence that the means are statistically different. So we just fail to reject. Say, okay, what this farmer is saying is true. So let's go back to our table. All right, so this is a two-tiered test.
Colin, sorry. Could we go back to the previous page? I think I was off for almost 5 minutes or so. My network. I just want to ask one question.
Here?
No. On the other table, just the one we've been working out now.
Yeah.
So you are saying minus 0.67 is inside.
Yeah.
How do you get there?
Zero is here. So you just use a number line.
Okay.
Yeah, 0.67 somewhere here. If it was negative 0.2 somewhere here. 0.15, just number line, the way the number line moves. If it was negative 10, it's
okay.
Just like, yeah.
Okay, all right, thanks.
Okay, so I want to now show you how an exam type of a question will look like. So in an exam, it will not come as easy as that. It will be a little bit complex. So we'll analyze this question in a wider context. So let's look at this question here. A farmer who has used a specific fertilizer knows that his average yield of tomatoes is 2.5 tons per hectare with a standard deviation of 0.53. The fertilizer is discontinued. He has to use a new brand. He suspects that the new fertilizer will alter the yield, but has no idea whether the change will be an increase or a decrease. At the end of the season, he finds that the average in the 5 plot has 2.65. At 5% level of significance, test whether the sample data is statistically different. So I want us to identify 5 things. Number 1, what can you see in there? What have we been given?
You.
Our mu, good. Our mu is what?
2.65.
Good, because no, it's 2.5. This is our average. Our mean. It has no sample size. It's an assumption. It's a historical mean. The 2.65 was calculated from how many plots? From 35.
Oh, okay.
So our x bar is what?
2.65.
Why is 2.65? Because it has what? A sample size?
Yes.
Of what? N, which is 35.
35.
What else are we given? So this n of 35 is what is qualifying us to use a z. If it was less than 35, we would have used a t.
Okay.
A t table. Then we're also given our standard deviation as what?
0.53.
0.53, good. And our level of significance is what?
5%.
So what does this tell you? 5%, it means it is what?
95.
Good, 95, which means our z is what?
1.6.
1.96.
1.96.
Yeah. Then he has no idea whether it will be an increase or a decrease. So this is where we're going to use this sign, equal to or not equal to. So it's a two-tailed test. If we had an idea that there'd be an increase, we would have used greater than, which is a one-tailed test. So I was saying, that's why I needed you to know this, to say our confidence level, our significance level, our alpha, our z for a two-tailed test, and our z for a one-tailed test. So who remembers? Quickly, let's all participate. Let's fill in this table. The signs that we use for a two-tailed test are equal to or not equal to. For a single-tailed test, either on the right or on the left side. So here we have 99. Then here we have 1%, 0.01. What is our Z?
2.5853.
And 98%, here we have what?
2.
Then here?
0.02.
And here?
2.33.
Good. And here, 95%. We have what?
5.
0.05.
1.96.
0.96, good. And finally 90, we have what?
10. 0.1. 1.6.
1.645.
645, good. This is for a two-tailed test. For a single-tailed test, this one goes up. We have 2.33 here. We have 2.05 here. We have 1.645 here. And here we have 1.28. The only difference here is when we are going to step 2, instead of dividing by 2, we are dividing by 1. That's how we get these figures. Otherwise, the rest is the same. Okay, so here it's a two-tailed because we don't know whether it will be an increase or a decrease. So step 1, state the hypothesis. So mu is equal to 2.5, mu is not equal to 2.5. Why are we using these signs? Because the farmer doesn't know in advance which direction. So we're using greater or equal to. The level of significance was 5%. Then our decision rule, we reject HO if it's greater than 1.96 or it's less than 1.96. Or we can just use this statement to cover for both of them. If Z, when you put absolute, meaning you're considering both the negative and the positive, is greater than that. So we reject HO. Then to calculate the test statistic, Z is X bar minus mu, standard deviation over root N. Our X bar is 2.65, our mu is 2.5, our standard deviation is 0.53, and how many plots were there? 35. So here we get 1.67. So 1.67 on our number line is somewhere here. Can somebody tell us, are we rejecting or we fail to reject?
We fail to reject. The acceptance region.
It's inside here, so we fail to reject, meaning we cannot reject here. So it means the question is asking us, is there a difference? This farmer wants to use a new fertilizer. Now, let me fortify on that. The farmer wants to use a new brand. Okay, so now the yield now and the yield before are not statistically different. So you're better off using what was what before, because this Z is inside. It means it's not effective. If you're a farmer and you're using certified seed, a 25 kg bag for certified seed gives you maybe 15 tons, and the uncertified 25 kg gives you 13 tons. That difference of 2 tons is significant enough. If you are finding your answer in here, it means no, I'm better off using maize seed, which is not certified. The yield is negligible. That is that. Now, if I were to use this question here, the weekly wage of semi-workers in an industry is assumed to have a mean population of what? 2.86. So this is our mu. There's no sample size. The standard deviation 29. The company pays a sample of 40 of its workers, an average of 271. So which one is mu and which one is X bar between 271 and 286?
271.
Yes. Why 271? Because
Does it sample size?
actually calculated from the what? The 40. So can the company be accused of paying inferior wages? So inferior is synonymous to what? Less than. All right. So it's single-tailed, it's not a double. How do we know it's a two-tailed or single-tailed? If the examiner says, is there a difference between the two mean pays? Then we know that it's a double, because the examiner is not biased in what he's asking. But where you're being asked, can they be accused of paying or underpaying or overpaying? Just know that it's synonymous to what? To a single or a double tail test. Any questions so far?
Yeah.
So are we clear so far? So here we are going to use a single tailed test, and the left one in that case, because we're using the word inferior. So it will be this side here. So if we're not given a level of significance, the standard is 5%. So I said 5% is the same as 95%. So for a double tailed 5% is 1.96, but a single tailed test is not 1.96. It changes. It is 1.645 by 5%. So although this is a lesson for another, but if you're able to grasp it even better. So this is the disparity that comes in. So you need to be so careful to understanding whether it's a single tailed or a double tailed test. So we're not going to use 1.96, we're going to use 1.645 because of the sign that's there. So these signs will be able.
So we need to master those as well.
Yes, you need to master this. Otherwise, you go through the steps that I told you. So I'm simplifying this as much as can be. You need to know. So let's go to our song here. It is important that you master this song. 2.58, 2.33, 1.96, and 1.645. This is for a two-tailed test. 2.33, 2.05, 1.645, and 1.28. This is for a single-tailed test.
You're saying single-tailed?
This one moves up and this one moves up. We have two new entrants, 2.05 and 1.28. All right. So step one, for instance, if you wanted to know for 90%, step one, find the level of significance, which is 10%. Step 2, for a double tail test, you divide by 2, which is 5%. For a single tailed test, you divide by 1, which still remains 10%. Step 3, subtract from 100, which is 95 here. Here it is 90. Step 4, convert to decimal, which is 0.9500. Then here, this is 0.900. So when you check in the table here, you find this at 1.645. If you check this one, you find it at 1.28. I'm not going to the table. I've already taught you how to do that in the table. That's where the difference comes in. All right. So if you had a question like this, suppose it is believed that civil servants get on average 5,000 kwacha. And when you sampled 49 civil servants, you found that they actually get 3,000 kwacha with standard deviation 14. At confidence level 90%, can you accuse the government of underpaying its workers? So underpaying, a synonym is what? Less than. So here you're going to put less than. So step 1, set the hypothesis. Step 2, the level of significance is what? 10%. Step 3, our Z. What is our Z at 10%? What is our Z?
1.645.
1.645. Anyone else?
1.28.
1.28. Why? Because of the?
Because we are talking about underpaying, so
it's a single
it's
tail
less
test.
than. We're talking about less than.
Yes, we're talking about less than. Good.
Yes.
So 1.28, because of this sign here, we're going to look at which tail, the left side. So here we're going to put 1.28. On the left side is always a negative. On the right side is always a positive. 1.28. Okay, then step 4, calculate our Z. So Z calculated is X bar minus mu, it's the same formula, standard deviation over root n. So our X bar is what? 3 minus 5. Standard deviation is what? 14 square root of what? N, which is 49. Okay. So minus what? 2. Then here, root of 49 is what? 7. 7 into 14 is what?
2.
Meaning our Z is what? Negative 1.
Negative 1.
So negative 1 is here, inside here. Right? So are we rejecting or we fail to reject?
Fail to reject.
So when we fail to reject, what does it mean? Is the government overpaying? We're simply saying there's no difference. The government is not lying. They're paying 3,000 and 5,000 are not statistically different. So we can't accuse them of underpaying. So they're within the claim. All right. That's what it means. So whenever you're failing to reject, it means there's no statistical difference. So I need you as much as possible to see how practice questions come in. Let me go through this one quickly. The specifications for extra large eggs have a mean of 125, the standard deviation 6. So here, 105, a sample of 24 repeated extra large eggs had an average of 123.2. The sampled eggs smaller than the specifications. So since it's smaller than, we're using this part here, less, all right? Okay. So our statistic, we start with x bar, which is 123 minus the mu, 124, then 6 over root of n. So we get negative 1.47. So I said whenever we're not given, the standard is what? Is 5%. All right. So at 5%, what is our Z for a single tailed test?
1.645.
Yes, 1.645. Then at 10%, what is our Z?
1.28.
1.28, excellent. So we can compare it at 1.645. Okay, so of course, I'll teach that. Would have loved the sample size to be. Sometimes the books will use. Let's do this question here together. Then we can end on hypothesis testing and leave the rest for later. Okay. Let's do this question together. I need us to participate. So we're given this question here. Okay. So standard deviation of salaries in a private sector is known to be 4,500, whilst in the public sector will be 3,000. A random sample of 80 people employed in the private sector has an income of 8 to 10, and a sample of 65 in the public sector has a mean income of 7460. Tests that the incomes of private sector are significantly higher than the public sector. So these are two samples. Whenever we're dealing with two samples, we have a new formula that we're going to look at. Okay, maybe this question, we can reserve it for later because I haven't taught you two samples. But from what we've discussed so far, are there any questions from what we've discussed so far?
Yeah.
It's clear?
Yes.
Okay. Please, this one requires a lot of...
Almost clear.
Okay. Let me look at another example. I think it'll help. Let me look at another example. Okay. Okay, here's another example we can look at for a single-tailed. Okay, this one here. A manufacturer claims that on average, his batteries last for 100 hours before they go flat. The population standard deviation of battery life is known to be 12 hours. We take a sample of 50 batteries and find that the mean is 95.5 hours. Does this sample mean undermine the manufacturer's claim? Okay. So what have we been given from there? We've been given so there are two means that are usually given. So I need you to identify which mean is it. The hypothetical mean or statistical mean.
The mu is 100.
Okay, the mu is 100.
And the x bar is
mu is 100.
95.5. Yes.
Okay. X bar is what?
95.5.
And 5.5. So our mu has no sample size. Our 95.5 was it calculated from a sample size of how many batteries?
50.
Of 50 batteries.
50 batteries.
Okay. Good. And our standard deviation is what?
12.
12. Okay. Have we been given a level of significance?
No.
So our standard is what?
95.
95.
Good. So meaning our Z, is it a two-tailed or a single-tailed test?
Two-tailed.
So two-tailed. So meaning our Z is what?
1.96.
1.96. Good. So let's go through the 5 steps. Step 1, our mu. So what is our mu? Mu is equal to what?
100.
100.
Then here mu is equal to what? 100.
100.
Step 2, what is our level of significance?
95.
Level of significance is what? 5%.
5%.
Then meaning our Z is what?
1.96.
1.96. So we're rejecting if it's less than the negative Z 1.96 or greater than 1.96. Then we calculate our Z. What is our Z?
Okay, so they do support 95.
100 minus 100.
Hold on.
100 minus 95.
So 100 minus 95.5. Calculate. Calculate the Z. On.
-2.66.
Negative 2.65. Oh, 66, yes.
Okay, positive. Yeah.
Okay, so what's our conclusion?
Reject.
Okay, reject HO. So by rejecting HO, what does it mean? Is there a difference?
Yes, there's a difference there.
Yes, there's a difference.
There's a huge difference.
Yeah. Okay, so